bus master architecture for chips with boundary scan. So, one possibility is that they are connected in a rings architecture. So, this bus master has got this TDI, TDO, TMS, this mode select and this clock signal. So, this what happens is that this application chips, so they are connected in a daisy chained fashion. So, as we have shown in the very first slides, very first few slides in the boundary scan technique, that the TDO of first chip is connected to TDI of next chip. So, that way it is connected. So, TDO of second chip connected to TDI of third chip, and finally, the TDO of the final chip comes back to the TDO of the bus master. And this test mode select line, so it is common to all the chips. So, all of them are doing the same mode of execution, and the clock signal is also common. So, that is doing this. So, this way they are connected in a ring form. So, they execute the same instruction in all the chips. So, we can have with separate test mode signal, like say if we want that different chips should execute a different test mode instructions, like some of them may be doing X test, some of them in test, some of them doing IR configuration. So, like that. So, if it is different, then we need to have a number of these test mode select lines, which are distinct for different chips. So, we have got one TDI and one TDO, that part remains same. So, then they are daisy chained. So, TDO is output connected to the TDI of next one and all that, but these TMS lines, so they are distinct. So, for each chip there is a TMS line, and this clock signal is common to all of them. So, that the test clock signal, so that is common to all of them. So, here separate separate chips can execute separate instructions. Can also have a start type of architecture, where we have got one bus master, but there are several such rings. So, these chips are in one ring, these chips are in another ring, these chips are in another ring. So, that way we have got 3 different rings. So, in a particular ring, so we have got TDI 1, test data input 1, and test data output 1. So, they are forming the boundary scan for the first few chips. For the second module, I have got TDI 2 and TDO 2 forming that chain, and third one TDI 3 and TDO 3 forming the chain. So, we have test clock signal is actually common to all of them. Here it is not shown explicitly, but the same TCK line is going to all of them, but this mode select line is different. So, all chips within the first ring they execute same instruction, similarly chips within the second ring they execute same instruction, like that. So, this is also a possibility if we have got large number of chips. So, if we want them to operate in different modes, then this may be the possibility of connecting them. Now, multi-drop architecture. So, multi-drop architecture means from this is like a bus. Okay. So, a test bus consists of these 4 lines TDI, TMS, TCK and TDO, and naturally we have got a multi-drop device connected to each bus. So, in this particular case what happens is this TDI signal is all these signals are transported over the bus. Now, there must be some sort of addressing mechanism. So, this multi-drop device, it must have some device ID, and by looking into this TDI bits, it should be able to understand like whether this operation is for this particular device or not. So, if it is for a particular device, then only this TDI line will be transported to the TDI of actual TDI of this boundary scan of these 4 chips. Similarly, if it is not that, maybe this device has been addressed. So, based on that address, so TDI line will be coming to this chip. Okay. So, that way it may be possible that we have got a multi-drop bus type of structure, but as we know that it makes the design simple, because I have got a simple bus from where a number of devices are dropping. But the problem is that since we have got a number of devices, so bus performance is going to be affected. So, you cannot drop a large number of devices from a bus. So, as it crosses say 8 or 10 devices, then it starts showing declination in the performance. So, that is another issue. So, bus master configuration with this multi-drop architecture. So, this can also be used in many cases. So, another possibility is a hierarchical organization. So, hierarchical organization, so this is 1149.1. So, all those lines that TDI, TDO, then your TMS and TCK, so all those lines are coming here. So, they are connected on a multi drop fashion on this, and so this is the first level of hierarchy, whereas if this TDO, so from this chip, chip, so it may be going to the next one, and that is forming the next level of hierarchy. So, it is so these devices, they are at the first level, then these chips, they are at the first level of this hierarchy, these chips are at the second level of hierarchy. So, this hierarchical architecture can also be used. So, it depends on the type of application that we have. If the set of commands that are required for testing, say this set of chips is less and less complex compared to the first one, then maybe this may be a possibility. Okay. So, whenever we are going to test this particular chips, all these chips are to be tested. So, in that case also it may be the thing that it is configured like this. So, this hierarchical architecture, so that can also be used. So, depending upon the application that we have, the types of chips and the way we are going to connect them, their physical location on the board. So, this hierarchical architecture may be beneficial. So, that talks about 1149.1 standard. So, there is another standard 1149.6, which we do not discuss in detail in this course, because that is some extension, like it has supported the high speed high speed test bus, then it has got analog interface and things like that. So, some augmentations have been done. Rather, we will look into another standard for embedded core test, which is known as 1500 standard. So, this 1500, so this is standard is similar to 1149.6, but instead of being applied at board level, it is applied at the chip level. So, it is a core test standard. So, we will look into this. So, the subdomains that we will look into is SOC test problems, what are the problems there, then architecture, what is the architecture, wrapper configuration, etc. So, what are the SOC test problems or requirements? First of all, what is SOC? So, system on chip based design is a way ahead, step ahead to the board level design. As I have told that in a board level design, we get the different chips from different vendors and we integrate them on a board. Now, if I have a board, then maybe on this board I have put a number of chips, and then these are various chips that we have, and we for testing purpose. So, these chips, they are said to be they are shipped into the market by the vendor, and they have done their own testing. So, naturally we can be confident about their correctness. So, these chips they may be assumed to be correct, but what we need to test is the interconnect between the chips. So, this interconnect, so this is a copper line running between two chips. So, that line has to be tested. Similarly, this may be another copper line running between the chips. So, that has to be tested. So, this way we need to test these individual chips, individual interconnects only. So, chip testing is not a major concern when we are going for this board based design, but the problem with board based design is that as we are trying to speed up, as we are trying to increase the performance of the system. So, it is seen that this off chip communication is at least 10 times slower than the on chip communication. So, if this happens to be the say the CPU and this happens to be the memory, then within CPU communication is much faster. As we know, the register access is the fastest is very fast within the CPU, but whenever the CPU tries to access memory, so it has to access using off chip bus, and then the speed drops. Okay. So, latency, though the CPU and memory both are semiconductor devices, it is due to the interconnect, physical interconnect that we have outside the chip, that may be a copper or maybe some other metal. So, that is going to introduce the delay. So, how to break this speed barrier? So, speed may be, this barrier may be broken if this entire thing is fabricated on a single die. Okay. Now, when we are doing that, when we are trying to do this thing, so I am not interested anymore in the chip available as CPU or chip available as memory. I am rather interested in getting the in getting some synthesizable descriptions of them, so that I can do my own manufacturing of the whole unit together. Okay. So, for that matter I have to go to different vendors, take their designs, but as soon as I say that, so it is contradictory, because no say no CPU designer company will give me their design as such, so that I can manufacture it. So, rather what they will give is some sort of a layout level description of the components. So, layout level description of the CPU, layout level description of the memory. So, if those layouts are manufactured properly, they are fabricated properly on a silicon die, then the whole thing will operate, and the as a system integrator. My role changes from designer, it becomes integrator. As a system integrator, what I need to do is to add some extra logic, add some interconnect between the devices, so that this whole thing is become the whatever I am looking for. So, that design is implemented. So, the major problem that we have is, now we have to mix up various technologies, like there are some logic design, some extra logic that I was talking about. So, some extra thing that is needed, so that has to be there. Then there are processor is there, memory is there, then we analog components. So, we will see later that this memory testing itself is a different domain. So, it does not follow the conventional fault models and conventional test techniques. So, for that I need to have a different type of test. Similarly, analog circuits, if we are going to test, then they require a different types of test. So, it is very much unlikely to have the expertise of all these techniques available at one place. Secondly, generation of test pattern is difficult, because I do not have the full detail of all these components. Okay. So, I cannot design a test ATPG process, so that test pattern can be generated for the processor, until and unless I have got the gate level netlist of the processor. So, naturally, so that stops an integrator from designing the test vectors or test technique for a particular component of this board, of this chip. So, what we have to do is, we have to rely more on the core developer, core vendors. So, they will also provide the test pattern, they will also tell how the test patterns may be applied, what are the responses, etc. So, we need various DFT, BEAST or other techniques. So, design for testability, BEAST, some of the cores may be beasted core. So, they have got their BEAST mechanism there. So, from outside world I need to just trigger the BEAST. Some of them may be having some particular type of scan chain configuration. So, from outside world I have to feed those scan chains with proper patterns. So, the requirements changes. So, unlike a design which is done in house and it is done by the single designer. So, here actually different vendors, core vendors. So, they have got their own DFT, own BEAST and all those things. So, bringing compatibility is a big issue. So, from outside world we have to do something, we have to add some extra thing into the system, so that it becomes, the whole thing becomes compatible and the test sessions can be run. Second important problem with this SoC based design is the embedding of codes. So, codes are often deeply embedded. So, as I was telling that maybe in this example itself. So, I have got this whole thing fabricated onto the chip, but I cannot say that this CPU is good. In a PCB level design or a board level design, I could say that the CPU is good because that is certified by the CPU vendor. Now, that is not the situation of the processor vendor, but that is not the situation. Why? Because if everything is fine about this particular design, maybe the silicon itself may be impure at that point. So, that way some fault may develop. So, since I am designing the whole chip myself, so the testing responsibility also comes. So, I cannot say that these individual components are fine, I need to test only interconnects. So, here the complexity is more, I have to test the chips, the components as well as the interconnects. So, if I want to test say this particular component, then I have to apply some test pattern. Now, how do I apply test pattern? The vendor of this particular module, this particular core, they have told okay, these are the 10,000 test patterns, if you apply and find the corresponding responses, 10,000 good responses. So, if it is all correct, then you know that okay, this is fine, my design is my design has been fabricated properly. Now, how to get rid of how to apply this 10,000 pattern? So, core vendor cannot tell, because core vendor does not know in which environment it is going to be put. Now, it may so happen that from the chip input, so if these are the inputs to the chip, from the chip inputs reaching this memory itself is a problem. Okay. So, that access may be difficult. So, for deeply embedded code, so it is very difficult that we find a functional path through the chips, and we can apply through the cores, and we can apply the pattern to the core under test. So, we need to have some sort of test access mechanism. So, it may be a functional path through the cores, or it may be some dedicated path. So, whatever we do, some test access mechanism has to be designed. Third important issue is the hierarchical core reuse. So, since today we are designing a system which is consisting of a number of cores. So, tomorrow if another system is designed where this system is a component. So, as a result we are going to reuse the SOC that we had designed previously as a core in the new design. So, naturally this previous SOC that we had designed, so it has got its own test structures in it, and those test structures we cannot change. Okay. So, they are remaining there. Now, for this new SOC that we are designing, since this is coming as a core, so for the new SOC this becomes a hierarchical testing. So, the first level cores are to be tested, and then for this IP reuse I have to use the next level of access mechanism. So, that way there is a hierarchical core reuse case. So, that will be there, and we need to have hierarchical test management policy. So, test access mechanism as well as the test scheduling algorithm, they should be able to take care of this hierarchy. Different code providers and SOC test developers. So, this is another problem, because this core vendors, so or core providers, they are having their own design, they have done their own test pattern generation or BEAST or whatever it is, or some DFT structure. But now, after that it is given to the integrator, or the integrators group will also have the test developers, which are who are working at the SOC test development work. But the problem is the interface between these two group of people. So, that is another issue. So, if there is no standard in this integration process, then it is very difficult to follow the whatever the test pattern or testing mechanism the designer has provided, and how to exploit it at the system level. So, this is another issue. And finally, the IP protection and test reuse. So, we need core test standard and documentation. So, this is another very important issue. So, without divulging the IP, how can we ensure that this IP can be utilized, its test philosophy can be utilized, and so this reuse IP reuse is a very important issue, and somehow under this SOC design paradigm, so we have to take care of this. Higher performance core pins than SOC pins. So, basically what can happen is that these SOC pins, so we have got maybe the SOC operates at some frequency, and when we are doing the testing in particular, so these SOC pins, they are operating at some frequency, but internally the cores, so they can operate at a much higher frequency. So, this higher performance core pins, so we so in those cases, those IP cores that we are talking about, which can operate at higher frequency, they must be done. For them we need to do a delay test. So, for that we need some at speed testing of those cores. Okay. So, that may be there. Then external ATE may be inefficient. So, the problem is that the ATE cost is very high, ATE cost is high, and ATE cost is dominated by mainly two factors. One is the memory size, another is the frequency of operation, the channel that we have, the number of bits that the ATE can send parallel to the test for testing. So, this makes this whole process very difficult. Okay. So this ATE is slow. Now, for a new design in my company, maybe I am doing a design at a high frequency, but the existing ATE is operating at a low frequency. So, I have to somehow test this chip with the available low frequency ATE, because ATE equipments are very costly. So, I cannot go for a new ATE just to test this new chip. So, there must be some mechanism by which I can use this low speed ATE, or inefficient, in that sense inefficient ATE, to do the testing of this high frequency chips that we have, or in some sense we can say we need some sort of on chip ATE. So, that is a very desirable situation, but it is very difficult to have. So, on chip ATE is difficult. At least at most we can have some sort of BEAST mechanism by which we can do a built-in self test of this individual code. So, that possibility remains, but otherwise it is difficult. Then long test application time. So, what has happened in the SOC design paradigm is that you see you have got so many components to be tested. Now, the IP vendors, they have provided us with a set of test vectors for each of the codes. Now, if this entire system was designed by a single group or single person, then they could have filtered out the test patterns, or they could have found out the test patterns which can test a number of faults in different components. So, that way there may be a possibility of doing a compaction of test set. So, we can identify which of the test patterns are very important, they must be applied, and which are not so important. So, that is possible only when we know about the design detail, how it has been designed, which part was taking care of the most important operation of this module. So, like that, if in the absence of those information, so we cannot do any pick and choose. So, what we have to do is simply apply all the test patterns that the vendor have provided, the core vendor has provided to the core under test. So, that makes the problem of this test time an important issue. So, we must this test time becomes very long. So, somehow we need to handle this problem. So, how can we reduce time? One possibility is to do parallel testing, which is test a number of modules parallelly. So, that way the test time will get reduced. Other possibility is do some sort of test scheduling. So, we schedule this testing into sessions, so that it is divided into proper time frames. So, we will have some test parallelism implemented. But this test parallelism has got its own problem as well, because the test power is another important part that comes. So, a number of modules being tested parallelly means a number of modules they are going to consume power. So, as we have discussed previously, that in normal mode of operation those modules may not be working simultaneously, but in the testing process, to reduce the test time, we have made all of them to work together. So, if we do this thing, then of course, there is a necessity to have high power consumption. It may be possible that all those power values are high. So, as a result they consume lot of power. So, we have seen lot of discussion on this test power minimization, but test scheduling is another way by which we can schedule these core tests, so that they do not consume high power. So, high power consuming cores will not be tested parallelly, or something like that has to be evolved. Then testable design automation. So, this is the tool flow that has to be created, so that given a design and these other parameters like these vendor specific parameters, then this whole testing process has to be automated. So, that is the other issue. So, these are the important problems and requirements for the SOC test issue, and we will see that how these problems will be addressed in the subsequent discussions. So, this is a typical view of this P15 this IEEE 1500 standard. Okay. So, we have got this sort of structure. So, these are the individual codes, code 1, code 2 up to code n. Now, these codes they have got this 1500 wrapper. So, every core is wrapped with this 1500 wrapper, so that from this interface it appears to be uniform. So, this interface will have some parallel inputs like this chip input output pins, which may be coming to this say core 1, and naturally they are to be passed through this P1500 wrapper. There you can understand that there should be some sort of boundary scan cell here through which these input will come reach core 1. Similarly, there will be some boundary cells here by which the core 1 output will go there. So, this way this cheap parallel input outputs they will be fed to different cores and they will go like this. Apart from that, we have got there may be other thing, in the sense that there may be some more mechanism by which the user can apply a number of test bits parallelly. So, that is known as a test access mechanism. So, this may be a user defined parallel test access mechanism. So, from test source, which may be some ATE channel or something like that, through some ATE channel maybe test patterns will be transported through this TAM, and similarly at this end we will have the TAM sync. So, that may again be the signal values response values going to the ATE. Okay. So, this way the user may define some parallel test access mechanism. So, from this parallel test access mechanism, this TAM in line, so they can come to this 1500 wrapper. Similarly, TAM out lines may be feeding this TAM lines. So, if the user has sent the test patterns into this TAM line, so this through this TAM in, it can reach this 1500 wrapper and through which it can be applied to core, or it may be possible this wrapper has got serial inputs, the WSIs. So, WSI serial input may be given from this serial wrapper serial port, and that way it can the test pattern may be fed serially into the boundary scan cells, and from there this boundary from the boundary scan cell, so it can be applied to the cores. Similarly, we have got a number of WSI and WSO lines for each chip has got one WSI line and WSO line, and they may be chained in some fashion, so that we can say that okay, these scan patterns can go serially through this chain, and there will be some wrapper signal controls which will be controlling this wrapper signal. So, how this shifting will take place, whether it will be parallel capture or serial capture, parallel transfer or serial transfer. So, all those things can be controlled by this wrapper control. So, this 1500 has to do this whole thing. So, it has to control both the serial part as well as the parallel part.